There are built-in functions that allow you to do hypothesis testing in R. In particular, you're looking for the function called t-test. You can query the help file here to get a sense what comes with the t-test. Basically going to be helping you deal with tests when you do not know the variance of the underlying population. You can do one sample test or two sample tests based on this. There are some examples at the bottom here which show you how you might want to do this. I'll tell you about some of the options available to you. For the sake of an experiment, let's say that we set up a small data set X, which consists of 1, 2, 3, 4, 5, 6, 7 observations. So this is our data set X. Now, if you wanted to test for whether the true mean from which this sample was taken was equal to 5, you would call the t-test function on the set X that you have observed, sampled, collected, and you want the mu to be equal to 5. So this is going to test for the null hypothesis that mu is equal to 5 against the alternative that mu is not equal to 5. That's a two-sided test where the underlying distribution in the population is unknown. So sigma is not known. Let's see what the outcome of this would be. I get all of the important information in that output. The critical value is there. It's minus 1.4412. I know the number of degrees of freedom. This is 6 n minus 1 for the test for the mean when I do not know the underlying standard deviation. That makes sense. The probability of wrongly rejecting the null hypothesis if it was in fact true, the p-value is given as about 20%, and the 95% confidence interval for the mean 3.84, 5.299093. Now what this is saying in many ways is that you can't reject the null hypothesis. It's conceivable, at least at the 5% confidence level, it's conceivable that the true mean is 5 because 5 lies in my 95% confidence interval. This is basically also saying that I cannot reject the hypothesis at the 5% confidence level because the p-value is 20% and 20% is greater than 5. I could reject it at the 20% level. 19.96 is smaller than 20%, but we don't usually ask for that kind of confidence. There's not enough evidence in the data to categorically state that the true mean is not equal to 5. And you also get the sample mean from this set of 7 observations. It's 4.571429. To give you an idea as to how this might, let's see what happens if we pick a different set, the set Y, that has 9 observations, and we'll test for the mean of this population of 9 observations, see if it's actually 5, see if that makes sense. And now we get a different output. Degrees of freedom is 1 less than 9, that's still 8. The critical value is minus 6.7823. The p-value is excessively small, and so the alternative hypothesis that the true mean is not equal to 5 is accepted here because the 95% confidence interval does not contain the value 5. P-value is small. The sample estimate is 2.444. This t-test, and it's a t-test because we don't know the underlying standard deviation, suggests that there's very strong evidence in favor of the alternative hypothesis that mu was not equal to 5. Now you might be wondering, say like the sample mean is 2.4444 here. We have evidence that the true mean is not 5, but what would it say about the true mean being 2.5? Oh, now we get a gigantic p-value. There's not enough evidence to reject the null hypothesis that the true mean of this data set of 9 observations is 2. If you're not interested in testing for the null hypothesis, say mu equals 5 against mu not equal to 5, but rather for mu greater than 5, then you would need to modify your t-test for the x value and say, yes, I'm testing for mu equals 5, that's my null hypothesis, and I want my alternative hypothesis to be that mu is greater than 5. So you need to specify that here. If you run this in here, you would get the following bit of information. P-value is fairly large. There is not enough evidence to reject the null hypothesis of mu being exactly equal to 5 in favor of mu being greater than 5. We just don't have the right kind of evidence. Then you can easily imagine that you'd want to do it the other way around. Here the p-value is a little bit smaller, and if you look at the actual values 4, 5, 4, 6, 4, 4, 5, there's a fair number of smaller values here than 5. In fact, 4 out of 7 in total, 5 if you include 5 in there as well. So it wouldn't be that surprising to find out that the true mean was smaller than 5, but the p-value is still fairly large, about 10%. And so at the 5% confidence level and the 1% confidence level, we cannot reject the null hypothesis that the true mean is actually 5. But the p-value, 10%, much smaller than the p-value for the greater than 5 alternative, which was 90%. And when you're testing for 2 independent samples to have the same mean, you want to use the following bits. So I'm going to still use my x and y as before. I'm going to test for x and y to have the same mean, assuming here that the variances are equal. So in the case of 2 independent samples, when I think the variances, yet unknown, should be equal. Let's see what the test tells us here. I get a very small p-value. I can reject with a fair amount of confidence that x and y come from populations with the same mean. A bunch of 4, 5, 6s, and here I have a bunch of 1, 2s, and 3s, a few 4s as well. Unlikely that they come from the same population. And if you want to test which one is likely to be greater, here it is going to test for the population mean of the first one, the x being greater than the population mean of the second one, the y. And we get a very small p-value that seems to tell us that it is quite certain that the population mean of the population from which the x samples come is larger than the population mean from which the y samples come. They're a very small p-value. We had a total of 7 observations in the first sample, 9 in the second sample, 16. The degrees of freedom here is 14 because we lose 1 degree of freedom to estimate the sample variance in each population. If you want to test the possibility that the population mean from the first population, the one from which the x sample comes, is actually smaller than the one from the second population, well, you will get the following result. Look at this p-value here. It's huge. It's almost 100%. So we can't reject the null hypothesis. Between you and I, we sort of know that mu1 is not equal to mu2, but it's not the way we read these things. Now I'll show you how you would do a paired 2-sample test. Let's pretend that we have a teacher who believes that a new teaching method might enable students to better understand elementary concepts. So she'll recruit 80 students to test her claim, and she's going to randomly assign them to one of 2 groups. Students in the control group A will be given the traditional lectures, and students in the control group B will be taught using the new method. And after 3 weeks, she will administer a short quiz to the students in both sections to see which of the groups have better assimilated the concepts, better understanding of the concepts, if there is even a difference between the 2. So the results of this study are found in the teaching.csv dataset. I will read it from the CSV file and just show them to you here. There's 80 such observations. The groups, the grades are there. Now x.1, x.2, these are just fake columns. They're in the CSV, but they're completely empty. So I'm going to stick to the actual columns that I'm interested in, which is the group and the grade. So now if I look at teaching, this is what it looks like. My students in my control group A and my students in my study group B. Is there enough evidence here to suggest that the new method is effective as measured by the test performance? You can summarize the results. First of all, what we need is a table that gives us the sample mean and the sample variance for each of the groups together with the sample size. So there's a little bit of code here that will do this. So we'll start by counting by group. We'll aggregate the teaching grade by the teaching group, the function here. What does that mean here? What do we have? we have an output of how many observations show up in each assigned group. That's 40 in each group. You can compute the means by group. We'll aggregate the grades by teaching group, and the function we use here is the mean. We compute the means by group. We get 75.125 in the first group and then 79% in the second group, and we'll also look at the variance. We get the following variances. A little bit more variance in the first group, a little bit less in the second group. I'll put all this together in one table using the tidyverse functionality. So I have to load tidyverse for this to make sense. Then I get a teaching summary. I'm going to rename the columns. And what does my teaching summary look like? This is the information that my control group A, my study group B, the sample size for each of the groups, n equals 40, the sample means in each of the groups, and the sample variance in each of the groups. If the researcher assumed originally that both groups had the similar background knowledge prior to being taught, and she tried to force that to happen by randomly assigning them to different groups, then the effectiveness of the teaching method, it's something that you can compute by comparing, by using a two-sample paired test. The null hypothesis here would be that mu A is greater than or equal to mu B, against the alternative that mu A is smaller than mu B. I use a null hypothesis which was, rather than just a point estimate, mu A greater than or equal to mu B. In the course, we basically saw mu A is equal to mu B. We have no real reason to suspect that the new method is worse than the old method, say. But in practice, it could quite be the case that the new method makes things worse. It doesn't actually change the test that you run. So what you need to do here is to compute the appropriate t-statistic for that test. And once you have the t-statistic, assuming that the null hypothesis is true, you will reject the null hypothesis in favor of the alternative if it turns out that the test statistic falls in the critical region, the rejection region for the associated distribution, and you'll fail to reject H null, which is not the same as accepting H null, if the test statistic doesn't fall in the critical region. Now we know what these things are going to be. We need to compute the specific test statistic for the two-sample paired test, the sample mean for the study group minus the sample mean for the control group, divided by this weird pool variance times the square root of 1 over the sample size in the control group plus 1 over the sample size in the study group. And once you have that, you will be able to decide if the test statistic is in the critical region or not. So how do you compute it? It's quite simple. Here we're going to hard code these things. We know what the number of observations in each group is. It's 40, but we'll go and get that information from the table so that we actually have an NA, an NB, and a total population size N. We'll extract the sample mean score from each group. Again, we know what it is. We'll just go and get it and place it into a specific variable y.bar.a and y.bar.b, the average grade for group A, the average grade for group B. We extract the sample variance of scores in each group. It's already been computed. It's in the table. We go get it. And then we compute using the NAs, using the number of observations N, A, and B, what the pooled variance would be, using the variance in each of the control and study group. So now we have all of the information we might be interested in here. 80 observations, 40 in the first group, 40 in the second group, the variance of the control group, the variance of the study group, and then the pooled variance, which is some sort of average, as you see, between these two quantities. And we get the corresponding t-statistic because we're estimating the variance. We don't know what the true variance would be. And the test statistic is 7.02. In order to decide whether we reject or not the null hypothesis, we need to compare this test statistic, this t-statistic value, to the critical value of the student t-distribution with 78 degrees of freedom, 2 fewer than the number of observations we have in total. And we need to pick a confidence level. So I'll pick alpha at 0.5%, my significance levels, my confidence level. I now find the critical value of the t-distribution with 72 degrees of freedom. And if I look at the value here, like, oh, I get a negative number. This isn't the one I was expecting because I'm testing on the other side. So I can get the actual proper critical value from the t-distribution with 78 degrees of freedom by specifying that I'm not interested in the lower tail value. I'm interested in the upper tail value, 1.66. Now, the test statistic that we've computed, t0, was 7.01. It is substantially larger than the critical value at 5%, 1.66. And then you would conclude that the null hypothesis should be rejected in favor of the alternative hypothesis. The data that we have, the evidence that we have suggests that the second method will help students achieve better scores on the tests. Assuming that everything else other than the way in which the course is taught has been controlled for and is the same. You're still not 100% sure that this is a better case, but if you use a confidence alpha of 5%, the data suggests very strongly that the second approach, the new approach, is better.